Welcome to Module 6, Part 0. It's about psychrometry. The prereq for this module is Module 5, Part 1, where we have done mixture of perfect gases, the PG mixture model we have covered there. In section 12.1 and 12.2 in your book, we'll find the materials that we are going to cover in this section. So let's begin with how we will describe air as a perfect gas mixture. So let's say we have a certain volume of air occupying volume V, and the mass of the air is m, and the mole of the air is n. Once again, let me remind you what a mole means. Mole means the count of molecules. So instead of counting the molecules in dozens, we count them in kilomole. A kilomole is a huge number, 6.023 into 10 to the 26. The exact number doesn't matter to us. It's a huge number. So we'll count molecules in mole or kilomoles and mass in kilogram, of course. And to describe air, we know that we can use PV equals nRT as an ideal gas equation of state, where P is in kilopascal, V is in meter cube, N is in kilomole, R is a universal gas constant, and T is in Kelvin. So we are all familiar with this equation. And when we have pure air, we'll treat air just like a pure gas. It will have a molar mass of 29 kg per kilomole. So this will be our standard molar mass of air. Then we can use this equation. Suppose we have pure air. Then we can write this equation, we can modify as N is what? Mass over molar mass, R bar T. Or we can write that as M R bar over M bar T, or MRT. So from here we can find the mass of air in a chamber if we know the pressure, volume, and temperature, and R becomes 8.314 divided by 29, and we are familiar with that. This is just for air, kg Kelvin. In psychrometry, in air conditioning, when we have this pure air, it is called dry air. So it's important to understand this terminology. Whenever we have air, in psychrometry, air can have moisture in it, so we will refer to pure air as dry air with a molar mass of 29 kg per kilomole. And we can use the ideal gas equation of state, PV equals nRT, to calculate the mass of dry air, etc. We'll soon see how it plays a role in psychrometry. But let's now switch over to another situation. Suppose we have a chamber, a rigid chamber, and let's say we completely evacuate it. It's totally vacuum. And now we inject some water into it. So we put some water here and watch what happens. So in the beginning, absolutely there is no pressure. And as pressure increases, you will understand that water will not stay. If there's vacuum here, some water molecules will come out, and we can understand that soon there'll be molecules of air here. So let's continue this thought experiment. Suppose we'll see the pressure increasing, and let's say the temperature is outside temperature, which is, let's just assume 25 degrees Celsius everywhere. So the temperature is not changing. So that this is the thought experiment. What will be the final pressure? That's my question. Suppose we have some water here. We make sure there is always supply of water at the bottom. So as time goes by, our question is, what is the final pressure? Will we agree that the pressure inside will keep increasing? We'll call this pressure of the water, we'll call it the vapor pressure, PV. The question is, in the beginning, PV goes from 0 to PV max. our question is, what is PV max? Now, it's a very difficult question. If you just start thinking from fundamentals, you would say, oh my gosh, I have to figure out how much water comes out, what is the volume, etc., etc. On the other hand, there is a very easy answer if you recognize that this water will seek equilibrium. As time goes by, at the end, the pressure will not change anymore. When the vapor pressure reaches its maxima, it's not that evaporation stops. There will be evaporation and condensation at the same time, and equilibrium will be reached. So just like if you put some ice in a bucket of water, and ice will start melting, but pretty soon an equilibrium will be reached. And if somebody says, what will be the temperature, you can easily say it will be 0 degrees Celsius. Here, what will be the pressure? That's our question. So the pressure, the answer would be what? It will be the equilibrium pressure. The answer is what? PV max equals the equilibrium pressure at, we know temperature is given, 25 degrees Celsius. If you recall the PC model, there is a direct connection between equilibrium pressure and equilibrium temperature, and that's called the saturation pressure. If you recall, P set at 100 kPa is 100 degrees Celsius, right? That's where we get the idea that water boils at 100 degrees Celsius. The real proof comes from the equilibrium of water vapor. If you put water vapor and liquid water at 100 degrees Celsius, you will find they will find a way to make the pressure to be 100 kPa. So when we boil water in atmospheric pressure, say in your kitchen, the water right above the water surface, when the water is boiling, the water vapor displaces all the air. So it's as if there's a pure water and water vapor in equilibrium. And that's what forces the temperature to be 100 degrees Celsius, because the pressure of the atmosphere is 100 kPa. So if the pressure, suppose you're boiling water in a mountain top and the pressure is 80 kPa, what temperature water will boil? The equilibrium, the saturation temperature at that pressure. So here we know the temperature 25 degrees Celsius. So what will be the PV max? PV max will be P sat at 25 degrees Celsius. And how do you find that? Well, you can go to the saturation table for water. We know the pressure. We know the temperature, so we go to the temperature saturation table, and if we go to 25 degrees Celsius, we can pick up the pressure. As you can see, 3.169. Let's call it 3.2 kPa. So the pressure is 3.2 kPa. So this difficult question we just answered, that is that if the vapor is at 25 degrees Celsius, the pressure will keep going up until it will reach 3.2 kPa. Okay, now what happens if there is air present? So let's do the same, continue the same thought experiment. We put some water in there and the temperature is fixed. Let's say temperature is again 25 degrees Celsius everywhere. The question is, if I have some air and we inject the water into the bottom of this chamber, what will be the maximum vapor pressure? Again, if the total pressure is P, then using Dalton's partial pressure, we can write total pressure is made up of dry air pressure and vapor pressure. So A meaning dry air. Remember, pure air is called dry air in psychrometry, and the pressure of water vapor. The question is, what is PV max? Well, one can again say it's a very complicated question to answer, but if you remember Dalton, what did Dalton say? If there's a mixture of gases, then you can treat them as if it's a superposition of individual gases, each having the same volume, same temperature, but different partial pressure. So this can be said equivalent to as if we have pure air at PA and pure vapor at PV, and each sharing the volume and temperature. This is the same. So So therefore, with a magic wand, we can just get rid of all the air molecules, and according to Dalton, nothing changed except the pressure will go from P to PV. So of course, that means the water molecules are in equilibrium with water vapor, oblivious of the presence of air molecules. So whether air is present or absent, PV max will be P set at T. So that's not changing, which we already saw. P set at 25 degrees Celsius, and we found that to be 3.2 kPa. So we know already from what we learned before, we just expanded that idea that if I have air and water vapor present, which is known as moist air, or just air made up of dry air and water vapor, and we understand the maximum water vapor pressure will be 3.2 kPa. So if there's a question that, in your room right now, pressure is 100 kPa and temperature is, say, 30 degrees Celsius. So if somebody says, okay, so what is find PA, find the pressure of dry air. How will you do that? If the temperature is 30 degrees instead of 25, we go to the saturation table. At 30 degrees, you can see the pressure will be 4.25, about 4.25 kPa. So you can say, okay, the water vapor pressure is 4.25 kPa. If 100 is my total pressure, PA will be 100 minus 4.25. So you can find the dry air pressure. So we just expanded the concept of water and liquid and vapor water in equilibrium to air where there is moisture present. Let me introduce a few terminologies now. The first one is that when the vapor pressure in the air reaches its maximum, PV equals PV max, it is called, then the air is said to be saturated air. So once again, what is saturated air? That when PV reaches maximum, then we say air is saturated. Air cannot hold any more water vapor. So I know you've heard of relative humidity. We'll soon move in there. But right now, just understand on its own that whenever air holds the maximum amount of water vapor at a given temperature, the air is said to be saturated. So if you just know the temperature, you can figure out if air is saturated or not. How? If the vapor pressure is equal to the saturation pressure, then it's saturated. But in general, air may not be saturated, right? Suppose here is moist air, which is not really saturated. So this is some moist air, let's say. So in this case also, the total pressure of air is made up of the dry air pressure and vapor pressure. And let's say PV is less than PV max. Well, it turns out that the vapor pressure in air has a lot to do with how comfortable we feel. But first, another definition. The ratio of PV to PV max plays a very important role to our comfort. We'll soon see why. And it is called phi, the relative humidity. You must have heard your weatherman talking about relative humidity all the time while talking about the condition of air. So the relative humidity, as you can see, if there is absolutely no vapor present, PV will be 0, obviously. There is no vapor pressure at all. Then, and at the most, PV can be PV max. So therefore, phi can go between 0 and 1, or 0% and 100%. That's called the relative humidity. So when relative humidity is 100%, the air is saturated. So phi equals 1 means saturated air, which means air cannot hold any more moisture. Whereas phi equals 0 means dry air. So we have a mathematical way now to say what is dry air and what is completely saturated air. So we understand also PV max is a function of temperature alone. So just to make sure you can figure out the relative humidity, so if you know the vapor pressure, which is always a little bit less than or at the most equal to PV max, and what is PV max? P sat at the temperature of the air. So from the given temperature, we can go to the saturation table, find the saturation pressure. That's the maximum pressure. So if you know the relative humidity, you can, from this equation, we can figure out the vapor pressure of air at a given time. Okay, so let's consider, let's figure out how relative humidity really connects to the comfort we feel with regard to condition of air. So let's have a thought experiment. Let's say we have air at 25 degrees Celsius and 50% relative humidity. Immediately we know that means the vapor pressure will be what? PV will be 0.5 times PV max saturation pressure at 25 degrees Celsius, and we already calculated that, you recall, 3.2 kPa. So this will be 1.6 kPa. So we have air with water vapor pressure of 1.6 kPa. Let's say we have a piece of cloth and here is a liquid droplet, basically a wet cloth drying. Obviously, my reference is, suppose you're sweating, we soon will translate this scenario to a practical scenario. Let's say we have a droplet here. Everywhere the temperature is 25 degrees Celsius, let's assume. So the droplet is also at 25 degrees Celsius. So imagine what will happen right next to the droplet. The vapor here will be in equilibrium with the water. And if so, the air will be saturated right next to the droplet. Of course, here humidity, relative humidity is 50%, phi equals 0.5, vapor pressure equals 1.6 kPa. But right next to the water, where the evaporation is taking place from the droplet, would you agree? Right there, the air will be saturated, and temperature being 25 degrees Celsius, the vapor pressure will be PV max, which is 3.2 kPa. So the difference in vapor pressure from the vapor right next to the droplet will drive a flow, and that's how drying takes place. The droplet will evaporate because of that. So this is called local thermodynamic equilibrium. In this zone, there is always equilibrium that exists. It's thermodynamic equilibrium. So even though the air is not saturated, it is only 50% RH, relative humidity, the water vapor, or the water vapor next to the droplet has a higher vapor pressure, and this pressure difference drive a flow. And that's how things dry. Whenever there's a pressure difference, you know the fluid will flow. So because of that, the drying takes place. So imagine if the relative humidity is 100% in the air, what will happen? The droplet will not dry at all because the pressure difference will be 3.2 kPa next to the droplet, and at ambient condition also you'll have 3.2 kPa. That's why when we sweat, we don't like high relative humidity. So if there is relative humidity is high, we start sweating, the droplets on our skin doesn't dry. But not suppose, to be fair, actually our skin is not at the same temperature as atmospheric, so the droplet temperature will be a little bit higher. So that's how a dryer works. Or when we put a piece of cloth in a sunshine, we know that it dries, even if the relative humidity is 100%. Imagine in New Orleans or Houston, where the relative humidity is almost close to 100% all the time, how will a piece of cloth dry when you put it, hang it out there in the air? The answer is that Many people think the wind drying it, not really. Sunshine falls on the cloth. As a result, the temperature here will be a little bit higher than 25 degrees Celsius. If your droplet temperature is higher, you can understand that the vapor pressure next to it will be higher according to the saturation pressure. And so PV will be a little bit higher here than the ambient PV, and that will drive the drying. That's essentially what happens in a dryer. When you put your clothes in a dryer, the temperature of the cloth is much above the ambient temperature, so the droplet temperature is really high, and therefore the vapor pressure next to the droplet is very high, and drying takes place. So essentially, the relative humidity is connected to our comfort because it's associated with drying. Imagine your skin, if there's a droplet of sweat, if it dries faster, you'll feel more comfortable. So the drier the air, the more comfortable we feel. But there's a limit. Generally, if the relative humidity is even lower than 50%, much lower, then we start sweating. We don't sweat at all. We go to the other extreme. We start losing water vapor quickly. So that's also not so comfortable. So in general, 50% relative humidity, typically you see in San Diego, is considered pretty nice to most people. Again, it can differ from person to person. Okay, so let's summarize. If we have moist air we'll typically just call it air, which is a sum of dry air and water vapor. The total pressure P, which is always 100 kPa, we'll kind of assume that, which is made up of dry air and vapor pressure. And the vapor pressure can be obtained if you know the relative humidity. It is PV max, and PV max is what? You recall, it's also called PG, or P set at the given temperature. So knowing the relative humidity, we can figure out the vapor pressure. It turns out that you can represent the state of the moist air in a PT diagram. Let me just explain. The temperature is also called the dry bulb temperature, essentially the temperature of the air. Why it's called dry bulb temperature, we'll discuss that later. So suppose if you know PV, the vapor pressure, and the temperature, you can detect the state of air because the total pressure of air is generally assumed to be known, 100 kPa. How does the maximum vapor pressure, suppose the question is that, suppose you want to, in this diagram, how will the maximum vapor pressure line look? What is maximum vapor pressure means? When the relative humidity is 100%. So you recall that at a given temperature, dry bulb temperature means given temperature, we can find the maximum vapor pressure from the saturation table. So if you know the temperature, suppose somebody's temperature is 40 degrees Celsius, then 7.38 is the maximum vapor pressure. So from these, we can plot, say, how the maximum vapor pressure changes as the temperature increases. So probably it will go something like this. So of course, recall that at 25 degrees Celsius, the pressure will be something around, we calculated that 3.2 kPa. So this is essentially the line of 100% relative humidity, because any state on this line means the vapor pressure is PV max. So along this line, PV equals PV max. So this is also known as psychrometric chart, where you understand that the air, the vapor pressure can never be beyond PV max. So the state of air will be somewhere, in this area. The state of water vapor in air will be somewhere in this area. So the psychrometric chart looks something like this, where phi equals 100% line looks like this. So suppose the question is, how will a phi equals 50% look like? So at a given temperature, we know, we can quickly say at a given temperature, this is the maximum PV. So when phi is 50%, we know PV equals what? PV equals phi times PV max. That's the definition of phi, which is P sat at T. So therefore, if we know the temperature, this would be phi equals 100% point, and 50% will be, PV will be half of that, so this will be my 50% point. So at each temperature, if I select my 50% PV, we'll get a new line, which will be phi equals 50% line. So in a psychrometric chart, the PV axis is not shown here. Generally, the PV axis is drawn on the right hand side. I mean, an axis can be shifted, and the temperature line or the dry bulb temperature line is at the x-axis, and so this is how a psychrometric chart is presented. Once you go to a chart, it is very easy. So suppose relative humidity is given to us 50%, and you know the temperature, you can read the vapor pressure and many other properties right off the chart. So what is the phi equals 0% line? Of course, when phi equals 0%, there is PV equals 0. So this line, this will be our phi equals 0% line. Okay, now that we have a few definitions, let's introduce a few more definitions, few more properties. Obviously, this is a mixture of perfect gases, and we can continue. Again, the total pressure is dry air pressure plus vapor pressure, whereas total pressure will be always assumed to be about 100 kPa. Psychrometric charts will be built on the assumption. And we can write for each component, if you recall our component properties, that according to Dalton's equation, P, volume and temperatures are shared. So dry air, we can write PV equals nRT, or if you use mass, it will become R of air times T. What is R of air? R bar over M bar. And we can write for the vapor the same ideal gas equation, except and mass of vapor RT, R of vapor, and R of vapor equals R bar over molar mass of vapor. So to introduce a new variable, it turns out that while solving problem, relative humidity is not as useful a quantity compared to something called the humidity ratio or specific humidity. So what is specific humidity? Is given by the symbol omega. It is mass of vapor divided by mass of dry air. So if you take any scoop of moist air, the mass of vapor divided by mass of air is called humidity ratio or specific humidity. So obviously for dry air, omega will be 0, and omega max will be corresponding to the maximum amount of vapor that we can the air can hold at 100% relative humidity. If we simplify, if we use the ideal gas equation that we have just written here, mass of vapor and mass of air, you can show that it will turn out to be PV over MV, PA over MA. It's relatively easy to show from these two equations, equation 1 and equation 2. You can show that mass of vapor divided by mass of air by dividing the two equations. And that can be written as, if I substitute the values of mass of molar mass of vapor is what? H2O's molar mass is 18 kg per kilomole, and molar mass of air is dry air is 29 kg per kilomole. So if you use these values, you can show that this becomes 0.622 vapor pressure And air pressure, by the way, we can substitute P minus PV because P is known. So as you can see, omega is a function of PV. So how would a constant omega line look in a psychrometric chart? Recall, in a psychrometric chart, we plot dry bulb temperature or temperature here, and on this axis we plot PV. So this is our 100% relative humidity line, and maybe 50% line will look here like this. So omega, as you recall, is given by a ratio. It depends on PV and total pressure. So obviously, if the total pressure PE remains constant at 100 kPa, which is assumed to be a standard pressure of air, then PV is a function of omega alone. So in other words, for a given PV, omega is fixed. So therefore, PV axis double as omega axis. In other words, we can plot omega in a parallel axis here, which will be something like this. Oops, let me pick up the pen. So the omega axis can be put right next to PV axis, of course with different numbers here. So if you can spot a state, suppose you know the temperature and relative humidity, so if you know the state, then we can read off what is vapor pressure and more importantly, what is omega from this axis. Let me introduce one more variable before solving a problem. It is the specific volume. Oh, well, specific volume is defined, or as you will see, most of the properties will be defined in a little bit different way. In general, you know, specific volume is volume per unit mass, but in case of moist air, the mass that we put in the denominator is the mass of dry air. Why is that? Because imagine if we went by the traditional thermodynamic definition of specific volume, then mass of air will be, mass of moist air will include vapor pressure, vapor mass. But the vapor mass is a variable. So if you're in your room, suppose you have right now, let's say, 1,000 kg of air, maybe out of that, maybe few kg is water vapor. And that number can change. Whereas the dry air amount usually don't change much. That's the basis on which air conditioning is made. We inject air, we inject water vapor, we take water vapor out when we condition air. So the basis becomes the dry air mass. That's why the definition is a little bit weird, but we still call it specific volume, and the unit will be what? Meter cube per kg of dry air. So this will be our standard way of representing specific volume. So how will specific volume lines look in this psychrometric chart? Well, recall, we already know from ideal gas equation of state that mass of air can be obtained if we know the the pressure of air, PV equals nRT, which is, we showed that equals mass of air, and this is the gas constant for air, by this formula. If we substitute in the above equation mass of air, you can easily show that specific volume becomes this, or we can write that as R of A, temperature of air, and the pressure of air, we can write the total pressure minus vapor pressure. So how will this a constant volume line, constant specific volume line look in this diagram? Okay, so suppose, one way to figure that out is say, suppose a given specific volume is a constant C. So C equals RAT over P minus PV. We know P is a constant, RA is a constant. So this will give us a constant times P minus PV equals RAT, or if we change side, P minus PV equals RAT over C, or PV equals, PV is on that side, P minus RA over C times T. So PV is our y-axis. I mean, axis where we place it doesn't matter. So it's like y equals a constant minus another constant times temperature is our x-axis. PV is our y-axis, so y equals mx plus c. So you can see the slope is negative. So you can go and convince yourself from what I have done here that a constant specific volume line will have a negative slope. So they will look something like this in this diagram. For each constant value, a diagram will look like this. So a scale can be made here for specific volume, and specific volume can be picked up right from the psychrometric chart. Just to give an example of the chart, if you go down into the MA model, sorry, it's in here. So this is where the psychrometric chart is. It looks quite complicated, but as you can see, we'll just concentrate here on, let's say, I know this chart is a little bit too big for my computer. Oh, I can change the size here. Okay, so you can see that this is the x-axis, the dry bulb temperature line or temperature line, and on this axis, as you recall, we have vapor pressure as well as omega we can read off. And these red lines are lines of constant humidity, the top one being 100, this one being 100%, and this is 0%. You can see 2%, 6%, etc. And you can also figure out the specific volume. See, specific volume lines are given like this. So this is 0.86 cubic meter per kg of dry air. So if you look at this chart carefully, you can see that given a state, you can always go and read right off what is the omega from this axis, y-axis here, or specific volume. And in the next part of this module, we'll cover how to find enthalpy and why the enthalpy axis appears here. And so given a state, if you can find the specific volume, omega, enthalpy, you are set to solve any problem. We'll see once we do the mass and energy equation, we can solve any problem. But before that, let's go and solve a simple problem involving the mass of water vapor in moist air.